Electromagnetic wave polarization. This is a very challenging subject to teach, and I've done my best to make this as visual as possible before moving into the mathematics. So let me know how I've done here. We'll start by just defining what wave polarization is. We'll talk a bit about these things called orthogonality and handedness, and that's really the discussion about which way things point. After that, we'll start getting a bit more specific and talk about different classifications of polarization, specifically linear, circular, and elliptical. It turns out we can point to all these different types of polarization and map them to a sphere that we'll call the Poincaré Sphere, so we'll also discuss that. After all this is where we'll dive really into the hardcore math. We'll touch on it before. And there's a form that I like to call the polarization explicit form. It's not necessarily the most compact mathematically, but it will make determining the polarization of a wave very easy. And we'll go through some examples. We'll take expressions for waves and dissect them and figure out all the different parameters, including polarization. What is polarization? So if you search on the internet, you will find that they all have essentially the same definition. It is the property of an electromagnetic wave that describes the time-varying direction and the magnitude of the electric field vector, or the electric field component of a plane wave. So we don't consider at all the magnetic field when it comes to polarization. Now, why is that? Well, that's because if we determine that we have a linearly polarized wave, circularly polarized wave, by looking at the electric field, we would come to that same conclusion if we looked at the magnetic field. So it is only necessary to look at the electric field. So here what we have is the expression for a plane wave in phasor form, and that initial term multiplying this complex exponential, that vector p that we've written, this is what we will call the polarization vector. So all the information about the amplitude of the wave and its polarization is wrapped up into that vector p. Why do we even care about polarization? Well, different devices, or even the same device, will behave differently depending on which polarization it's been excited with. Sometimes they can behave profoundly differently. Take polarized sunglasses, for example. They behave very different depending on which way the light is linearly polarized when they're going through them. That's just one example. If we're interested in any sort of interference, orthogonal polarizations will not interfere with each other. Another way this comes up is sometimes we want things to interfere. For example, let's say we have a remote control airplane, and if we put an antenna on it that is orthogonally polarized to the antenna that you're holding to control it, those antennas won't talk to each other. So understanding polarization is very important from that perspective. If we're looking at devices on the scale of a wavelength, or even structures on a device that are on the scale of a wavelength, polarization becomes critical. It is possible when the devices are hundreds of times larger than the wavelength that we can start thinking about these waves as scalar waves. Not always, but many times. So people that study imaging and lenses and microscopes, really polarization doesn't come into play in these things a lot of times. Now when they really try pushing the focus down to tiny spot sizes and things like that, polarization does become important. Well, that's because we're talking about things on the scale of a wavelength again. So focusing properties of lenses can be different based on polarization. Reflection and transmission from an interface can be different. I'll bring up the polarized sunglasses again. When light reflects off of water or windows, it tends to reflect in a way that's polarized. And so we would buy polarized sunglasses that would block the polarization that's dominantly reflected from water or glass. And so we say it reduces glare, and it does do that. Resonators, so clocks in our circuits or microwave sources and many other things, the frequency of these resonances can be very different based on polarization. Cutoff frequencies for things like filters and waveguides can be different for different polarizations. Let's talk briefly about the orthogonality and handedness of the polarization of electromagnetic waves. So in linear, homogeneous, and isotropic media, so we'll call those LHI media, it turns out the electric field, the magnetic field, and the direction of the wave, all three of these are exactly perpendicular to each other. So since the electric field and magnetic field are both perpendicular or transverse to the direction of propagation, we would call these waves TEM. Now, if we relax any of these things, we go into anisotropic or inhomogeneous media, for example, then these don't necessarily have to be perpendicular to each other. Very often they're close, but they don't. There's some interesting things that happen, but that's outside of the scope of this course. So we will say that an electromagnetic wave obeys the right-hand rule. So the little picture that just popped up, you'll see that if you point the thumb on your right hand in the direction of the wave, that's K, your index finger in the direction of the electric field, then your middle finger will point in the direction of the magnetic field. And so we would call this a right-handed system. Just to prove that the electric field is always perpendicular to the direction of the wave, let's start with Gauss's law, del dot D equals 0. The first thing we need to do is put this in terms of the electric field. So we replace D in Gauss's law with epsilon E. And so that's the constitutive relation. Now we have our divergence equation in terms of the electric field. Well, that permittivity term, the epsilon, that's a constant. That can come to the outside of this equation. Well, we can divide both sides by epsilon, and we end up just with del dot E equals 0. The next step, let's plug in the expression for a wave, because the electric field is our polarization vector times this complex exponential, which is our plane wave oscillation term. If we calculate the divergence of our expression inside parentheses, we see that a minus jk comes to the outside. So we end up with a minus jk dot p times e to the minus jk dot r. So we divide by all of our constants on the left-hand side. So that's the negative, it's the j, it's the exponential, and we're just left with k dot p equals 0. Let's remember what we know about dot products. Remember, this is actually a test many times, and if we can see that the dot product between two vectors is 0, that means they have to be perpendicular to each other if they are 0. Well, our Gauss's law has told us that K has to be perpendicular to the polarization vector. Our polarization vector is the electric field, thus we conclude that the electric field is perpendicular to the direction of the wave. The proof that the magnetic field, H, is perpendicular to the direction of the wave follows the exact same thing. We start off with Gauss's law for magnetic fields. We will then put that in terms of H. We will bring the permeability to the outside. Now we can divide both sides by permeability. And we get del dot H equals 0. We substitute in our expression for the magnetic field component of a wave. We take the divergence and the minus jk comes to the outside. Now we can drop all of the constants and we get k dot h equals 0. Again, if the dot product of two vectors is 0, it has to mean that they're perpendicular, and our conclusion is that the magnetic field H is perpendicular to K. So E is perpendicular to K, H is perpendicular to K. We have yet to prove that E and H are also perpendicular to each other. To do this, we start with Faraday's law. We will plug in the expression for the plane waves, both for the electric field and the magnetic field. We take the curl on the left-hand side, and the minus jk comes out in place of the del operator. And we simplify this, we end up with k cross E equals omega mu times h. Now let's solve this for the magnetic field. And so we get k cross E over omega mu. The important thing here is the k cross E in the numerator. Remember the property of a cross product. If we take the cross product of two vectors, the new vector that we get from that is perpendicular to both of those vectors that we took the cross product of. So since we are calculating h from a cross product containing E, that has to mean that h and E are perpendicular to each other. Now, we could have just started with Faraday's law and said the same thing. Here's a cross product of two things. Clearly, H has to be perpendicular to E. We went through all this work because it might be a little confusing with the del operator there. Does that property still hold? Well, it actually does, but maybe it's a little bit more abstract. So we went through the work and we showed that E is perpendicular to H also. So the conclusion is E, H, and K are all perpendicular to each other. And that is a TEM wave, a transverse electromagnetic wave. Polarization classification. We're going to look at what linear, circular, and elliptical polarizations actually are. A linear polarization is any time that we have a wave where the electric field is oscillating in a straight line. So here I'm trying to visualize a wave, and this is actually really difficult to do. So these sort of faded out rectangle looking things, what I'm trying to visualize there is these amplitude fronts or phase fronts of the wave. And these are actually infinite slabs in the x and y directions, and that's really tough to draw. And so the blue line, the wavy thing you see along the z-axis, that's the electric field exactly along the z-axis. Now, we're showing these vectors extending away from the z-axis, and it's important to remember that we're not talking about a phenomenon off of the z-axis. We're talking about a phenomenon that is occurring exactly on the z-axis, but since it has a direction and an amplitude, it's really hard to draw and keep it also exactly on the e-axis, so we're forced to have these vectors go up and down. So aside from that, notice the electric field here is oscillating purely along the x-axis. The wave itself is traveling in the z direction, but the electric field is oscillating along the x-axis. Remember, the electric field always has to be perpendicular to the direction of the wave. So x and z axes are perpendicular. Now mathematically, here's how we're writing it. Of course, we have our oscillation term, the e to the minus jkz, and using the negative sign convention, that is talking about a wave propagating in the positive z direction. Now our polarization vector is a larger expression inside of these parentheses, and it has some amplitude term E naught and a direction. Here's the x direction. So it's oscillating with an amplitude of E naught in the x direction. So that is a linearly polarized wave, and we would call it linear polarization, or LP for short. We could just as easily have the electric field oscillate in the y direction. So the only thing different now is that our electric field is in exactly the y direction. It's still oscillating along a single line, so it's still a linear polarization. Mathematically, the only thing that has changed from the last slide is the subscript on the a unit vector, showing us that this unit vector is in the y direction now instead of x. But our oscillation term, e to the minus jkz, that's the same. The amplitude term is the same. Everything's the same except the electric field is oscillating in the y direction. And of course, the y direction is still perpendicular to the z-axis. This is still a linear polarization. So we actually have at least two possibilities, linear polarization along x and y. it turns out there's even more possibilities for directions. Here, what I'm trying to show is that the electric field can oscillate along any direction as long as it is a single direction. And so if we pick some tilt angle theta off of the x-axis, we can write our polarization vector a little bit differently. We'll give it a cosine theta in the x direction, a sine theta in the y direction, and we'll move this amplitude term to the outside, this E naught, and we have the same oscillation term, e to the minus jkz. So we just have a slightly more complicated polarization vector now. But that is still a linear polarization. It's just that the electric field is oscillating now in a direction defined by the angle theta. And here I'm defining that angle theta off of the x-axis. So when theta is 0, this cosine theta is 1, the sine theta is 0. So when theta is 0, we only have oscillation along the x-axis. And we saw that. When theta is 0, our electric field was oscillating solely along the x-axis. And in fact, our theta is coming around now to being theta equals 0 right now, or we just passed through exactly along the y-axis. And we're going to return to 0 in a minute or a few seconds, and the electric field will be oscillating purely in the x direction. So any of these directions defined by theta is still a linear polarization. On to our next type of polarization, and this is called circular polarization. What we're looking at now is, put aside for a second that there's this thing called circular polarization. We know that we can have a linearly polarized wave along x and a linearly polarized wave along y. What I'm showing here are these two waves happening at the same time and just coming together so that they're overlapping. So our x polarized wave is in green. We'll call that E1. So its polarization vector is E naught in the x direction. And our y polarized wave really has the same expression, except we're calling it E sub 2. And of course, its polarization vector is E naught sub AY. Now what we'll do is we will change the phase of one of those linear polarizations relative to the other. So here we're taking the oscillation along the y-axis and we're adding phase to it, or we're pulling it backward relative to the polarization along x. And look at what happens to the overall wave. That's what's shown in blue. As long as those two, the red and green waves, the x and y linear polarizations, as long as they're in sync and in phase, we get a linear polarization along their diagonal. But notice as we bring them out of phase, when they become 90 degrees out of phase, if we look at sort of the composite overall effect on the electric field, we see that it's doing this corkscrew or helix type pattern. That is what we call a circularly polarized wave. But a circularly polarized wave really is nothing more than just two linear polarizations that are 90 degrees out of phase. And depending whether we add or subtract the phase, we'll end up getting right-hand circular or left-hand circular. And that's something that we'll talk about in a few slides. So all we've done is added two linear polarizations, and then we added 90-degree phase to the y direction linear polarization, so we retarded it by 90 degrees, and we got an overall circularly polarized wave. So when we add these together, here's a slightly cleaner way of writing this. Just a amplitude of 1 in the x direction, another amplitude of 1 in the y direction, but this j is here giving it a 90-degree phase. And so what we'll do on this illustration here, we'll fade out the two linear polarizations, and we'll just think of this as one composite wave that is circularly polarized. But it is perfectly correct to still always think about a circular polarization as two linear polarizations that are 90 degrees out of phase. One more time before you want to reach through the screen and strangle me. A circularly polarized wave is like two linear polarizations 90 degrees out of phase. Now we could be plus or minus 90 degrees of phase. So in the general setting for circular polarization, we have to write a plus minus here because we could have plus or minus 90 degrees of phase. Let's talk more about whether that is plus or minus. This is where we get into right-hand circular and left-hand circular. So if we have a plus in that equation, this is what we call right circular polarization. And a way to think about this, imagine we are observing this wave from behind it. So the wave is moving away from us in the z direction, and we're observing which way the electric field is rotating. So if those eyes are our own eyes, the electric field appears to be rotating clockwise. So at the top it's moving to the right. So a clockwise rotation as we watch the field move away from us is what we will call a right circular polarization or right-handed circular polarization. Either of those work. So of course the opposite is true. If we have a minus sign in here, that means that the rotation of the electric field will now be counterclockwise. The wave is still propagating in the z direction, but as we're observing the electric field with a wave moving away from us, it appears to be rotating counterclockwise. So at the top of that it moves left, and we call this a left circular polarization. We also have elliptical polarization. What is elliptical polarization? That just means it's not linear and it's not circular. So everything else is elliptical polarization. I might even argue that everything is an elliptical polarization. If that ellipse is really, really tight, notice the short axis here. If that short axis, as it tends towards zero, we get a linear polarization out of our elliptical polarization. Then if those two axes of these ellipses, if they become equal, in other words, its width stretches out to equal its height here, well, then we'll have a circularly polarized wave. So really, linear polarization and circular polarization are just two special cases of elliptical polarization. Otherwise, there's not really a strict definition of this. It's just if it's not linear and not circular, it's elliptical. But we could say if we were to observe this wave as it's moving away from us and watch the electric field circulate, it's tracing out an ellipse instead of a straight line or a circle. Now this is another useful way to think about things. Let's think of what I like to call continuum of polarizations. So what we're looking at here is not the Y-polarized wave propagating. We're looking at two still waves. They're not moving, but what I am doing is just taking that Y-polarized wave and just sliding it to the right. I'm just adding phase to it. And how much phase am I adding? Well, mathematically, I'll call this delta. So we're just adding two linear polarizations and just adding a little bit of phase. So they start off in sync, and then we just slide that. What happens when we do this? The blue is the continuum. You notice the overall, the blue wave started as linear when the X and Y polarizations were in sync. When they got 90 degrees out of phase, the overall passes through a circular polarization. If it keeps going and we end up 180 degrees out of phase, we're back to linear again, but the linear is actually 90 degree rotated from the original linear. So that's right about there, where the width of the ellipse goes to zero. We get a linear that's been 90 degrees rotated. So overall, here's what's happening. We have two linear polarizations. When they're perfectly in phase, we get a composite linear along their diagonal. As we slide the phase of one relative to the other, the overall composite wave passes through a continuum going from linear through a bunch of ellipticals to circular, then through a bunch more ellipticals, and then back to linear but 90 degrees rotated. So it's really a continuum of polarizations as we slide the phase of one of those original linear polarizations. I feel like I just botched explaining that, but there's a continuum here, and I think that's a useful way to think about this. There's another continuum when we have two circularly polarized waves added together. So I am showing a green and a red. The green has a right-hand circular polarization. The red is left-hand circular polarization. And what I'm showing here is not the red wave or the LCP wave propagating. I'm just adding phase to it. So we have two circular polarizations, and I'm just taking one and adding phase to it relative to the other. What does the composite wave look like of adding those together? Well, it turns out if we add two circularly polarized waves, we get a linear polarization. And the phase between those circularly polarized waves tells us the tilt of our linear polarization. And we can show that mathematically. If we expand out the right-hand side of this first equation, collect common terms, etc., we end up with our expression for a linearly polarized wave at tilt angle theta. So, two linear polarizations together, if they're plus or minus 90 degrees, we get a circularly polarized wave. As we slide the phase of one linear relative to the other, we get a continuum of polarizations that go from linear to elliptical to circular to linear to elliptical and back and forth. If we have two circularly polarized waves and we change the phase between them, we always get linear. However, the tilt of that linear depends on the phase between those circularly polarized waves. So this is a different continuum. We can't add two circularly polarized and get elliptical. We're always going to get linear, but the tilt of it depends on the phase of the two circular waves. Now let's talk about a neat concept called the Poincaré Sphere. The Poincaré Sphere, well, it's a sphere, obviously, and all possible polarizations map to a point on the surface of that sphere. Now, at the North Pole, that corresponds to a right-hand circularly polarized wave. The South Pole corresponds to a left-hand circularly polarized wave. The equator of this sphere is our continuum of linear polarizations. So at 0 degrees, we'll have a vertical polarization. So we rotate around. When we rotate 90 degrees, our polarization has rotated 45 degrees. When we rotate around to the back, our polarization has rotated 90 degrees. So notice it is perpendicular to the original polarization. So every 90 degrees we come around the equator, our polarization rotates by 45 degrees. And of course, when we come all the way around, we're back to where we started. So the equator is our linear polarizations. North and South Pole exactly are the right and left-hand circular polarizations. Everything else is our elliptical polarizations. Now, why does that matter? Well, if we have some weird elliptical polarization, and I ask the question, what is orthogonal to it? Or I might even ask, here's two polarized waves. Are they orthogonal? Will they produce interference? That's kind of a difficult question at first. But if we have a Poincaré sphere, if we are at opposite sides of the sphere, those two polarizations are exactly orthogonal, and they will not produce interference with each other. And that makes sense. North and South Pole are at opposite points. Right and left-hand circular, they are orthogonal. They will not produce interference. If we're along the equator, the 0 degrees, and at the opposite side at 180 degrees around the equator, gives us a 90-degree rotation of the polarization. Of course, these two linears are opposite, and they are orthogonal, perpendicular. They will not interfere. These other two linear polarizations, those are rotated relative to each other by 90 degrees, so they are orthogonal or perpendicular, and they will not produce any interference. And if we're at any 2 points on the sphere, as long as we're at opposite sides, those polarizations are perpendicular and will not interfere. Here's a neat visualization of this. So we have the Poincaré sphere drawn to the left, and this little red dot is just some point on that sphere. And as it walks around, I'm visualizing the corresponding polarization on the right. So what you'll notice at the north or south pole, when the red dot is there, we have circular polarization. When it passes through the equator, it becomes a linearly polarized wave, and everywhere else it is just some sort of elliptically polarized wave. So there really is this nice continuum of polarizations. So I'm going to let this movie play a bit so you can fast forward through this if you don't want to hear this, or if you want to keep watching it, you're welcome to just keep watching it. I'll let it play until it repeats. Okay, I think we went through the full cycle and it's repeating, and that dot is just walking around arbitrary path along the outside of the Poincaré sphere, so don't do too much thinking about that, but just watch the position of the point and the corresponding wave that we get. I think it's a pretty neat visualization of the Poincaré sphere. So let's move on. Now we're going to dive into the math and talk about what I call the polarization explicit form. So we know that the electric field is perpendicular to the direction of the wave. That means that our polarization vector can be in any direction perpendicular to K. And that's what I'm showing here. This circular plane here is where our polarization vector should exist. So I can pick any two directions, A and B, as long as A and B are perpendicular to K, and also A and B are perpendicular to themselves, and I can describe our polarization vector this way, as some number multiplying direction A plus some number multiplying direction B. I can write my polarization vector this way. So remember the rules for picking A and B. A, K, and B have to all be perpendicular to each other. There's also a handedness that we have to satisfy. A cross B, that cross product, has to be in the direction of K. We don't do that, then we're going to get a negative sign where we don't want one. So any choice of A and B will work as long as it's satisfying those two rules. Given A and B, we can now write our polarization vector as just a weighted sum of those direction A's, A and B. So P sub A is the amplitude in the A direction, and P sub B is the amplitude in the B direction. And PA and PB, those are complex numbers. They can be out of phase with respect to each other, and we'll need that when we start talking about circular or elliptical polarizations. So we are originally writing our expression for a wave this way. Our polarization vector times our oscillation term. And this is for a wave traveling in the K direction. But now we can write our polarization vector with more terms there. We're expanding this into A and B directions. So in general, PA and PB are complex numbers because those two linear polarizations in A and B, they can be out of phase. So our PA is a real valued amplitude term times an e to the j phi a, where phi a will be the phase of the polarization in the A direction. And similarly, P sub B is a real amplitude number times e to the j phi b, where phi b will be the phase of the polarization in the B direction. So now we can take those expressions for PA and PB and plug those into our expression for the wave. So we no longer see PA and PB. We have everything in terms of the EA, EB, phi A, and phi B. Now what I'll do is take this phi A, this exponential term, e to the j phi A, and factor that out to the outside. So notice in the A direction now we no longer have a phase term. The B polarization now has a difference between those two phases, and I brought phi A to the outside. So in a way, we're sort of pretending that that's the common phase between our two polarizations. We're going to interpret the phi B minus phi A as the phase difference between the A and the B directions. And as I mentioned, the phi A, we're going to interpret this as the common phase, the phase that's common to both the A and the B polarizations. So given delta and theta, we can now write the expression for the electric field component of our plane wave this way. And this is the final expression. This is the polarization explicit form. And anytime we have any kind of expression for a wave, we're going to want to write it in this form, because then we can determine its polarization very easily. Without doing that, it can be much more difficult to determine polarization. So that's step one. If we want to determine polarization, put it in this form. So here's the rules. The first thing I will do is I will look at this delta term, the phase between the A and B directions. If that is 0, without even looking at EA and EB, we immediately have a linearly polarized wave. So anytime delta is 0 degrees, we have a linear polarization. And what we could extend this to, if it's 180 degrees, 360 degrees, negative 180 degrees, negative 360 degrees, those will all be linear polarizations. For simplicity, I'll just say 0 degrees means a linear polarization. Now, if it's not 0, I'll next look to see if it's 90 degrees or 90 degrees plus some kind of integer multiple of 180 degrees. But let's just call that 90 degrees for right now. If it is not 90 degrees, then we immediately have an elliptical polarization. So first we check for 0 degrees. If it is, it's linear. Then we look if it's 90 degrees. If it's not 90, then it's elliptical. Once it's 90, I realize, okay, we may have a circularly polarized wave, but not necessarily. We now have one more thing to check when that delta is plus or minus 90 degrees. What we have to check is the magnitude of EA and EB. If they are the same, then we have a circularly polarized wave. If they're not the same, we have an elliptical polarization. So I'll repeat the process. The first thing I do is look at delta. If it's 0, it's linear polarization, we're done. If it's not 0, then I go ahead and look, is it 90 degrees? If it's not 90 degrees, or not 0, it's elliptical. But if it is 90 degrees, then I suspect we have a circular, but we have to check the amplitudes to make sure the amplitudes in the A and B directions are equal. And when they are, that is a circularly polarized wave. The very last thing I'll do is I'll look at the sign of that 90 degrees. If it's a positive 90 degrees, we have a right-hand circular polarization. If it is a negative 90 degrees, we have a left-hand circular polarization. So once we're in this polarization explicit form, it's very easy to determine the polarization. Let's go through some examples, and let's start dissecting plane waves and pulling off their various parameters, including polarization. So example number 1. We have a plane wave, and I've written the expressions here for both the electric and the magnetic fields. What can we learn from this? Well, if we look at this omega term, that's the angular frequency. That is related to the ordinary frequency through omega equals 2 pi f. So we can read off the angular frequency and calculate the ordinary frequency. The ordinary frequency, that's the term that's in units of hertz, kilohertz, megahertz, gigahertz, terahertz, and everything else. So that's an easy thing to do. So we have ordinary frequency. Given the ordinary frequency, and we know the speed of light, we're able to calculate the free space wavelength of that wave. The next thing I'll do is look at the wave vector. And we can tell the direction of the wave by the direction of k. So I just wrote that as a unit vector here. If we're smart enough, we don't really have to get the unit vector. We can just tell what direction the direction k is in. But this unit vector, that's all that conveys is direction. So I wrote it that way. So from the wave vector, we can determine direction of the wave. If we look at the magnitude of the wave vector, that's the wave number, we can get the wavelength of the wave. And that's because the magnitude of our wave vector is 2 pi divided by the wavelength of the wave. Now this is not the free space wavelength, unless our wave happens to be in vacuum. This is the wavelength inside whatever medium the wave is in. And so depending on the refractive index or the speed of the wave, that wavelength could be long or short or whatever. So it changes depending what medium the wave is in. Now we can determine the speed of the wave because it's not necessarily the speed of light. If it's inside of a medium, it's probably slower. But the speed of the wave is frequency times wavelength. Well, we've just calculated those two parameters. So we've determined the speed. There's two ways now that we can calculate the refractive index of the material that this wave is in. One of them is the ratio of the free space wavelength to wavelength. That will give us the refractive index, and that's because wavelength changes in proportion to the speed of the wave and refractive index. If refractive index is higher, the speed is slower and wavelength is reduced. The other way we could calculate refractive index is the ratio of the speeds. So speed of light divided by the actual speed of the wave inside whatever medium it's in, which we just calculated, gives us refractive index. So there's two possible paths for determining the refractive index. Now we'll focus our attention on these amplitude terms. So we have the two complex amplitudes, H0 and E0. And so these terms in blue are actually what we would call the complex amplitudes, because what we've done is we've separated amplitude information from the actual direction of the polarization. That's why I'm writing K and P as unit vectors. So we just have a unit vector down here too. So the blue H0 and E0 are our complex amplitudes, which have the amplitude and phase information in them. And what's in black is our polarization information, the direction of the polarization. So the ratio of those two complex amplitudes, E0 and H0, that gives us the impedance of the medium. If we know impedance and we know refractive index, well, here's how our permeability and permittivity are related to refractive index impedance. So if we solve these two equations for our relative permittivity and relative permeability, now we can calculate those. So think of all this stuff that we just pulled out of those two expressions for a plane wave. Now I know there's not real numbers here, but in a practical situation, you might have real numbers here. We can start calculating all of these things just by looking at the expressions for the waves. So the information of E and H tells us all of this different stuff: speed and frequency, refractive index, wavelength, impedance, all of that. It's pretty neat how that works. Now let's do numbers. So here's an expression for the electric field. The first thing I will always do is put that in standard form. I didn't say polarization explicit form, I said standard form. The polarization explicit form would manipulate this polarization vector a little bit farther. But this is the standard form for a wave. And once we do that, we can read off all these various parameters. So clearly, comparing these two equations, What is in parentheses here is our polarization vector. We can read off our angular frequency, 2.4 times 10 to the 9. And the units here for angular frequencies, radians per second. Now, reading off the wave vector is a little bit more work here. And notice the negative sign here. That's due to our negative sign convention. But this term over here is k dot r. So over here, all of this stuff is somehow minus k dot r. Because the minus sign is here, I think it's easiest and most straightforward to first factor out the negative sign from these remaining terms. So here's how I do that. We keep our 2.4 times 10 to the 9t. That doesn't have anything to do with what we're doing right now. We'll bring out a negative sign and write all of the other stuff. So what is in parentheses here is our k dot r. So k dot r, without numbers, is kx times x plus ky times y plus kz times z. So if we look at this, the expansion for our dot product of k dot r, and we look at what is inside the parentheses, we can read off what is kx, what is ky, what is kz. So in this case, kx, which is multiplying x, is a minus 5.1. There is no y over here, so ky must be 0. The term multiplying z is a positive 3.5, so kz is 3.5. Then we can tie all this stuff together, and we can finally get our wave vector. And its units are inverse meters. So that took a little bit more work. The real trick is we had to factor out the negative sign and then compare it to the dot product, the kx times x plus ky times y plus kz times z. But we got our wave vector.